Hi everyone. In this video we're going to revisit the topics of mass, center of mass, and the inertia dyadic. This time, instead of using the infinite summation, we're going to use integral calculus. Once we go through these three equations, write how to find these, we're going to do three examples, and we can actually do these examples fairly quickly. We're going to do a block, a cylinder, and then if you take a parabola and rotate it into 3D, we're going to do that problem. So let's go ahead and get started, and let's start with mass. Let's start by talking about density. We know that density is mass divided by volume, and we can of course rearrange this and solve for the mass. Mass is density times volume. What we want to do is we want to approach this using integrals. Perhaps we don't know the volume, and the volume is defined by some functions, etc. We need to look at this as differential. So the differential bit of mass is going to be the density multiplied by a differential bit of volume. Now, the density doesn't have to be constant. We could also rewrite this as density being a function of the position. So I've drawn a representative body over here. We've broken it into little bits of mass. This was our discrete approach. What if we replace this b sub I with instead some little differential bit of mass? So we are taking the volume and we're breaking into little differential bits of volume. So we have options with respect to coordinate systems. We know that we have Cartesian, and we know that we have cylindrical, and we of course have spherical. So when we write d volume, let's write it as volume so there's no confusion with velocity. So when we write this term d volume, the way that we're going to do this and the approach for this differential bit of volume is going to depend on how we set up our frame. Are we defining this in Cartesian or cylindrical or spherical frames? So d mass, bring down the density. Okay, so what about in Cartesian coordinates? This differential bit of volume gets replaced with dx, dy, and dz. And I'm going to go ahead and give you cylindrical as well. X, y, z. If you're doing this in cylindrical coordinates, it is r times dr d theta dz. And recall that in cylindrical coordinates you have the radius, you have the angle that you're going to reflect around, and then you just have the height. So Cartesian on top, cylindrical underneath. Now, how would we get the mass out of this? Well, just integrate. So the mass is going to equal, we're going to integrate that differential bit of mass. And again, perhaps we have some function for the density, and perhaps the shape of the container. We have some function for that as well. So this is really where the we could describe it using a single integral. We could say density, and I'm just going to use parentheses to represent these. So we could have density d volume, and we're going to integrate over that volume. And for example, if we're using Cartesian, then this is the triple integral from some bounds on the x, some bounds on the y, some bounds on the z of that density times dx, dy, dz. All right. So we've got these working definitions now for calculating the mass. Next, let's take this and let's talk about how we can use this to find center of mass. So recall from previous discussions, we know that the center of mass, the position vector from N to A, we know that this is the weighted average of the positions. So let's say infinite summation. So a moment ago I had b sub I. Let's use the b sub I. This is going to be the weighted average of all of these position vectors from n to b sub I multiplied by their individual masses, and then we take that and we divide by the total mass. Okay, this was discrete. We want to do this for continuous systems. How is it going to be different? We're still going to divide by the mass. This time the infinite summation is going to be replaced by the integral. And this position, we're going to lose these this sub I notation, so P into B, all of the infinite points that we could calculate. So let's say we're going to integrate over the volume. And now instead of the mass of B sub I, now we're looking at that differential bit of mass. So dm. Now, what are we going to do? Let's do a little bit of replacement here. Let's say that the position vector from n to b, let's call this x in the x hat A, and y in the y hat A, and z in the z hat A. So we're going to take this and we can plug it in right here. And then recall from just a moment ago, we had an expression for this differential bit of mass in terms of the differential bit of volume. So let's take these two things and let's put them into that equation. So P in A is going to equal, and I'm going to set this up as a fairly large division. Recall that we need to divide by the total mass. Okay, we said that that is the, and let's say for now we're doing, let's say we're doing Cartesian. So we're doing a triple integral over the volume, and this is going to be the density multiplied by dx, dy, dz. So again, this is the total mass. Next, we need to do the triple integral of, and recall the position vector was x in the xa plus y in the ya plus z in the za. So let's say right now what we're writing is we're writing just this first part. So this answer is the x hat A component of the center of mass, and then we're just going to say plus dot dot dot. So that's for the other two terms. So we need to take the x, and that's our position vector, and then we multiply by that little differential bit of mass. And we know that if I cover up this triple integral, that was the differential bit of mass. So it's x multiplied by, here is our density, multiplied by all of those. So this then is how you find the location of the center of mass using calculus. Triple integral, sort out these details, and then that's it. Okay, so we took care of that. Next, let's talk about the inertia dyadic. Recall that when we derived the inertia dyadic, that was also using a discrete formulation. We said that the inertia dyadic was, we had an infinite summation of the mass, NBI, multiplied by, and then we had this dyadic. And this was, tell you what, there, that's better. If we want to do this with calculus, instead of doing an infinite summation, we know that this summation gets replaced with integrals over the volume. We have a definition for the mass, and we know that the mass is going to get replaced with this differential bit of mass. And all of these little sub-i's, these sub-I notations, these are going to get dropped. So the way that we resolve this inertia dyadic is we can actually take it one term at a time. What if we wanted the IXX term out of this, let's say this is the AA inertia dyadic. If we want this IXX term, that's this first one, this is going to equal, and again, let's suppose that we're doing Cartesian coordinates. It's the triple integral over the volume, so over the x, y, and z bounds. You have these coordinates, so y squared plus z squared multiplied by the density. I'm just going to leave the density. We know it could be a function multiplied by dx, dy, dz. If you wanted the izz term, then instead of y squared plus z squared, you would have x squared plus y squared. And that's literally it. So the difficulty now, the tricky part, comes in with figuring out what kinds of coordinates you want to use, right? Do we want to do Cartesian? Do we want to do cylindrical, etc.? And then just sorting out the details of the triple integral. So let's clean this up and let's go through 3 examples real quick. First example, let's calculate the inertia in the XX for this block. So we had the equation from before. We know that the inertia in the XX, we're going to need to do a triple integral. We're going to have the coordinates y squared plus z squared. And then let's say that the density is a constant, dx, dy, dz. Now what about the bounds? I've drawn the axes coming off of the corners, and we could mathematically get away with doing the bounds 0 to the length and 0 to the width, 0 to the height, etc. Formally, if we're doing the bounds to the to the left and right and before and after the center of mass, then so length is associated with x. So really, formally about the center of mass, this is negative length over 2 to length over 2. Width is in our y direction, so negative width over 2, and the height, h, is our z, so negative h over 2 and h over 2. All right, let's take care of the x first. So if we integrate over the x, first I'm going to pull this constant density out. Then we're going to be left with x evaluated on the bounds. And I'm just going to write this as this bounds delta x. We know that it's from negative length over 2 to length over 2. I just get tired of writing it. And then I'm actually going to break up this double integral so that we can see the steps very clearly. Let's say the double integral, and I'm just going to write delta y, delta z. So y squared dy dx plus, and I'm just going to erase a little bit of this, double integral over delta y, delta x, sorry, delta y, delta z, there we go, delta y, delta z, and now we have our z squared dy dz. All right. Let's take care of this. If we evaluate the x from length over 2 minus negative length over 2, we're going to get density multiplied by the length. Next, let's go ahead and in this first one, let's resolve the dy. So that's going to yield y cubed over 3, and we're going to evaluate this at those same bounds. So I'm just going to say delta y. And then this is multiplied by, we have this leftover integral of dz plus, let's resolve the dz on this one, so that leaves z cubed over 3 evaluated over those bounds, and then there's the leftover integral dy. All right, next. Let's just consider what's going to happen when we evaluate just one of these. So if we can actually pull out the 1/3, but this is this y cubed evaluated on these bounds. That's like writing, let's see, y is width, so that's like writing width over 2 cubed minus negative width over 2 cubed. Okay, so that is width cubed over 8 minus negative width cubed over 8. And that is, of course, negative with negative makes this positive. These will add, and that is going to make width cubed over 4. So that's what happens when we evaluate this one. Now the 1 over 3, well, let's go ahead and start building this. I'm going to factor the 1/3 out of the whole thing. So density times length over 3. And then we have this width cubed over 4. And then we're still going to have this, this last integral, dz plus. Now, same thing's going to happen with the z cubed. We would have height over 2 cubed minus the negative height over 2 cubed. So we're going to get a similar form. We're going to get height cubed over 4, integral of over the dy, over the delta y, and then here's our dy. Okay. Next, let's take care of these last integrals. So ixx is going to equal. Now what's going to happen here, we're going to have a z term, right? And we know the bounds of z is negative h over 2, negative h over 2 to h over 2, and that's going to yield h. And the same thing's going to happen here with the y. We're going to have a single y term, and then over those bounds, negative w over 2 to w over 2. Here's what we're going to get. Density times length. We can factor out the 4. Of course, 4 by 3 makes 12. And then we're going to be multiplying by w cubed times the height plus height cubed times w. Now, at this point, consider we can factor out of each of these terms one w and one h. So ixx equals, I'm going to write density times length times width times height over 12, and then what we're left with is w squared plus h squared. Now we're looking at a block, so length times width times height, that's the volume. Ixx is the mass, let's just call it mass of A. Mass of A over 12 times w squared plus h squared. All right, so blocks are easy. Is it any more difficult to do a cylinder? I don't know, let's find out. When we evaluate the cylinder, we could use Cartesian coordinates if we really wanted to. We could put this cylinder inside of a box, and then we could shave off the mass around those edges through constraints. An easier method is just to do a change of variable and convert from Cartesian coordinates into cylindrical coordinates. So instead of looking at x, y, and z, we're going to replace that with the dimensions z in the vertical, and then radius and the angle theta around. So recall that cylindrical coordinates is really just polar coordinates plus the vertical. And we know that our differential mass this time is going to be a function not of little differential squares, but this time these are actually shell elements. So the change now, this is our density as a function of x, y, z. Consider that's cylindrical coordinates. So you could be looking at density as a function of, instead, r theta and z. And now it is r multiplied by dr, d theta, dz. So this is our new differential mass term. And this time when we calculate the inertia, let's do the inertia about that this long axis. Let's find the inertia around the cylinder. So now we're looking at the IZZ term. So again, we have the triple integral. Since we're doing it about z, we're looking at x squared plus y squared. And density, we're going to say density is constant multiplied by r, dr, d theta, dz. Clearly, we're going to have to do some change with the x squared plus y squared. We'll get to that in a moment. The bounds for the radius, let's go 0 to capital R. We'll use that for the radius. For theta, we're going to go around, so 2 pi. And then for z, we're going to go negative h over 2 to h over 2. We'll start at the center of mass and we'll split it. Now, if you recall from polar coordinates, x squared over y squared, this is equal to r squared. So our calculation now is the triple integral over r squared multiplied by r. Well, that's going to make it r cubed dr d theta dz. Same bounds on the integrals. Okay, let's do the dz first. So the bounds on the z, negative h over 2 to h over 2. You integrate, you're going to get a single z over these bounds. That's going to give us h. And let's go ahead and pull the density out as well. So rho times h. 2 integrals left. We have r cubed dr d theta. Oh, I wrote ixx, gosh. ZZ, there we go. Okay, so IZZ, density multiplied by h. Next, what we say these are? 0 and capital R, 0 and 2 pi. Let's do the integral with respect to theta. So that's going to give us a single theta from 0 to 2 pi, so that's going to give us 2 pi. And here is the last integral, 0 to r of r cubed dr. So IZZ now is equal to density times h times 2 pi. This is going to be r to the 4th over 4 over the bounds 0 to r. And that, of course, is just capital R to the 4th. So IZZ is going to equal density h 2 pi r to the 4th all over 4. So we can do a little simplification. Consider the volume of a cylinder. Well, it's the surface area of the bottom multiplied by the height. And the surface area is going to be pi r squared. Specifically in this case, we're looking at capital R. So let's isolate the volume. And let's say density multiplied by pi r squared multiplied by height. So we know that that's going to be density times volume. And what's left? Well, we took out the rho, we took out the h, we took out the pi, and we took out 2 of the r's. 2 over 4 is going to leave a 1/2. And there is pi multiplied by r squared. So IZZ for the cylinder, about that z-axis, this is the mass. So 1/2, oh gosh, I forgot yeah, we took the pi out already. There we go. 1/2 times the mass, so let's say mass of A, multiplied by the radius squared. Okay. Again, the only thing really tricky here is sorting out what coordinates you want to use and what your bounds are, etc. Let's do one that's slightly more complicated next. For this last example, I've drawn a parabola in 2D. Imagine that this parabola has been rotated about this vertical z-axis so that in 3D it forms a dome. We want to find the inertia of this dome, parabola, about its z-axis, so the IZZ term. So we're going to use cylindrical coordinates. I've gone ahead, I've drawn the radius. It has a maximum height h, and I've written the equation for this curve. So the height z is equal to the maximum height h minus the r squared. And that equation does show us that there is an implicit constraint between the height and the radius. The radius squared cannot exceed the value of the height. And as the radius squared approaches the height h, then this dome, this parabola, becomes very short. Our approach is the same. We're looking at the triple integral, and our bounds for this one are going to be 0 to r on the radius, 0 to 2 pi for theta, and for the height, let's go from 0 up to, and we're going to input this equation that we have, h minus r squared. So we know the equation, we know that it's density multiplied by, well, let's write it this way. It's the x squared plus y squared. Now, we're going to do this in cylindrical coordinates. We know that x squared plus y squared, we know that this is equal to r squared. Now, it's that multiplied by the differential mass. So here's our density. We're going to say the density is constant, and now we're going to multiply by r dr d theta dz. So we can, of course, simplify this a bit. Not x. Izz, we've got the triple integral, and we can combine the r's. So r cubed times density dr d theta dz. Same bounds on the integrals. Let's do the easy one. Let's do the d theta first. So we can pull the density out. We're going to multiply the bounds on the theta was 2 pi, and now we're left with two more integrals. I'll write the bounds for these, 0 and h minus r squared. Inside of the integral, we're still looking at r cubed times dr dz. Next. Next, let's do the integral of the dz. So dz, this one's going to put it in terms of r, so we need to keep it inside of the integral. So density times 2 pi, here's that last remaining integral 0 to r. If we bring down, consider that there's going to be a z, and z is over the bound 0 to h minus r squared. So we're effectively just multiplying this r cubed by the h minus r squared. So we're looking at h r cubed minus r to the 5th times dr. All right, Izz, density times 2 pi. Now, when we integrate this, we're going to have h r to the 4th divided by 4 minus r to the 6th divided by 6. And this is over the bounds 0 to r. So, rho 2 pi times h capital R to the 4th over 4 minus capital R to the 6th over 6. Now, this one is a little bit messier, and we could actually simplify this quite a bit. As we had done in the previous problems, we could go back and we could take the equation for the volume of this shape, and we could use that to extract terms, and we could convert the density into the volume. I'm just going to leave it at that for this one. If you want, you could, of course, you could find the volume of this. You simply integrate over all three of the dimensions. Okay, so this is how you find inertia of bodies if you don't have any software, right? You could always look up the known geometric shapes in a table. If you don't have a known geometric shape, but you have equations defining it, you can always plug those in and solve for the inertia. In modern day engineering and modern day design, what is mostly done is we use software like CAD software, so SolidWorks or Pro Engineer, something like that. And if you have some strange-shaped body, and this is not defined with some given functions. It could be a structural part with all kinds of material bored out of it. What really happens in CAD software is it takes this geometric shape and it breaks it into all of these discretized sections using nodes. And when it does that, it covers this whole geometric shape in a mesh. And then what it will actually do to find these is it will actually go back to the discrete definitions where we said IZZ is equal to, and we said the discrete form of this was MBI times, so we're doing about Z, so that's XI squared plus YI squared. And consider, in software, if it's applying a mesh to this, then you have some discrete differential bit of volume, and the computer software can find the centroid of that little differential bit. So it knows, numerically it knows Xi and Yi, and it can also find the amount of volume of that little bit, and then it finds that little volume and multiplies by the density of whatever material you selected. So in modern day CAD software, this process is actually done numerically. Of course, how good is the answer? Well, the accuracy of the answer is really a function of how fine of a mesh you've applied. So if you apply a large mesh, then your answer is so-so. If you apply a medium mesh, it gets a little better. And if you apply a very fine mesh to this, very fine mesh, you're going to approach, we could say, the true answer. Your answer is going to become more accurate, or you could also consider it as more precise as well, because as you approach it, you're going to get more decimal points of accuracy. So you always have these theoretical approaches to fall back on. Modern day design, if you have access to software, of course, just use the software. Okay, so that's it for this video. I'll see you next time. Best of luck.